Hello again. So I am back again to finish that lecture on graphene. So today we are going to talk a little bit about quantum transport theory of graphene. So let me get started. So before we get started, I just want to introduce a little bit of a classical quantum Hall effect. So then that can lead to quantum Hall effect, and later in the next lecture I will talk about topological insulators. In that we can introduce even more subtle effects like spin Hall effect and anomalous Hall effect and things like that. So it's a good point to start talking about classical Hall effect. So classical Hall effect is like it is shown here. So we have this uh, material. So where we have conventional current flowing from left to right. So in the current I. So that means you have electrons flowing in the opposite direction. We know the conventional current is basically the flow of positive charges, right? This means your electrons are flowing in the opposite direction. Now, if I apply a perpendicular magnetic field to the current and the plane of the material, so then you will see these electrons will undergo something called Lorentz force. So due to the Lorentz force, they will move to in both perpendicular to B and I direction. So then in the process, it will start accumulating charges on the two opposing phases. So, but we cannot have this charge accumulation happening indefinitely. So to stop that, it will apply an opposing field. So we call the Hall field. So that Hall field will stop further accumulation of charges. So in order to calculate that Hall field or Hall voltage, first we will consider what is the force applied on this moving charge. Suppose this charge is moving at a velocity of v. Now if I have a magnetic field B, we know the Lorentz force is given by the charge times v cross B, the cross product, right? So we can write the charge Q will experience a Lorentz force in the lateral direction. That means perpendicular to both B and I. So given by Q V cross B, but V and B are perpendicular. So that means B, your angle is 90 degrees, you get sine 90 is 1. So you get that Lorentz force as QV times B. So now, like I said, so due to this force, electrons will start to accumulate on this surface because they will undergo this circular motion. So, but the whole field will oppose that accumulation. Suppose that whole field is EH. So then if you know that electric field, we know what the force is, right? So that force is given by Q times that whole field. So like I said, as more and more carriers are deflected, the accumulation of charge produces this whole field that imparts a force opposite to the Lorentz force. So this is the whole field EH. If the charge is Q, then the whole field is given by charge times that whole field. So we know at equilibrium these two forces are equal. Then I can write QVB equals Q times H. From here we can see Q and Q cancel. Then you can calculate your V, that is given by EH over B. So this V we call the drift velocity or drift speed. So now if you know the current density, we know this current I. So then the current density means the current divided by the area, right? Perpendicular surface area. So in this case, your area would be this W times your thickness T. So your thickness is given by T, this one, and the width is given as W. So then this area is given by W times T. So also we know the current density is given by NQ times V, right? N is the charge per unit volume. We call the charge density. Q is the charge and V is the velocity. So now we know V here, EH over B. If I substitute here, NQ, V is EH over B. That is the current density. Now we define something called the Hall coefficient. So Hall coefficient is defined as EH divided by J times B. So in this case, EH divided by J times B means 1 over NQ. So this is the definition of your Hall coefficient. The Hall field per unit charge density per unit magnetic field. That's how we define the Hall coefficient. So that is given now as 1 over NQ. You can see this Hall coefficient has a sign of Q. So that means if you have electrons as your charge carrier, so then Q is negative, then your RH will be negative. If holes are the charge carriers, so then holes have the sign of positive charges, so that means RH will be positive. So that's why I think Hall coefficient is a good indication whether your dominant charge carrier is holes or electrons. So now we can actually calculate this RH in terms of your Hall voltage. Suppose your Hall voltage is VH, so the corresponding to EH. So then EH is given as VH divided by W, right? That's the potential gradient. So we can write, that's the definition of RH, EH over JB. So then EH you can write as potential gradient VH over W. W is the distance between those two parallel planes, right? So where the charges are accumulated, that's the width. So then J is the current divided by the perpendicular area, that is W times T times B. Now you can say W and W cancel. So then you get VH T divided by I times B. So then also we know RH is given by 1 over NQ. So then if you can write actually VH as then IB divided by NQ times T. So you can see when your charge density is high, your VH is going to be very small, right? That's why the metals have very high charge density. That means your Hall voltage is very small. So like I said before, so RH determines the sign of your charge. Okay, so this analysis actually we can do a little bit more in details, because that is helpful when we going to talk about quantum Hall effect. This is a classical Hall effect, right? So let's do this classical Hall effect in little bit more details. Suppose when you have this electron moving in an electric field and magnetic field, so then we can write the general expression. Your total force is given by minus E times E plus V cross H. Actually, this is written in CGS units. That's why you have this velocity of light here. In SI units, you don't need to consider C. So then your total force is given as, this is the force due to the electric field. So that is going to be related to the whole field later, right? Then we have the applied magnetic field. So this is the Lorentz force. So then also we know your force is basically dp over dt, right? So that's a rate of change your momentum. So it's given by E. Then V I can write as momentum divided by m, because P equals mv, right? So cos h. Now we know in the relaxation time approximation, dp over dt is given as your total force minus P over tau. This is we call the relaxation time momentum change. So that is tau is given by is the relaxation time when electrons collide with another impurity or phonons or something like that. So then that electron will velocity will go back to 0, then start again to accelerate, right? So that time tau is called the relaxation time. So then dp over dt you can approximate by this term coming due to the relaxation of the electron after the collision. So now in the steady states, so we can write this equation. You have dp over dt becomes 0 for the steady state. So, but you have component for px, p as px and py. Then h is only in the c direction. So h has only c direction component, but p has both px and py. So e also has ex and ey, right? So in both directions. So, but in the under steady state, dp over dt becomes 0. Now, since you have this p cross h term, so you have to take the vector product, because p has two terms, px, py, h has only c direction h field, then you can do that vector product. So if you do that one, you can separate the two x and y terms. So then you get two equations. One come in as, because this is 0 minus eax. This comes from this cross product. Then this one has px over tau. Same thing for the y term. So this is 0. Then you have minus ey. Then you get the cross term. You get x term, right? You have cross term here, px. Then you have py over tau. So here this omega c I just wrote as EH over m. So that is basically cyclotron frequency, if you remember. So now these two equations, I can just multiply by this Ne tau over m and use this J as Ne V. V is P over m. And also we know this something called the Drude conductivity, that is given as this longitudinal current and electric field by the Ohm's law. Jx is given as sigma 0 Ex. So, but sigma 0 is Ne squared tau over m. That's the Drude conductivity. If you multiply this one and arrange the terms, you get these two equations. E0x, this is from the x term, but you can see jy term coming from this cross product term. Then you have this term. So if we know in the Hall field, so since you have this electron accumulation, the Hall field is to oppose that accumulation. So that makes this jy 0, right? So at the end, so if I apply jy 0 here, then you get ey as this one, because jy is 0. That's the opposing Hall field to stop further accumulation of charges. So then if you write sigma 0 as Ne squared tau over m and substitute all these things, so you get minus h over NEC times Jx. So now if you remember, your Hall coefficient is written as your E divided by J times B, right? So if you do that one, your RH is given as minus 1 over NEC. That's your Hall coefficient. Now you get the same result, but a little more general analysis. So here is the summary of that, what we talked about, your in the SI units. So this is your cyclotron frequency B over m. So this is the Drude conductivity, N squared over m. So J is given by your E and V, V is P over m. So this is the two equations, right? Ex over Ey. So if you write this way, so then your we call that Hall resistance given by this V over E NL. So if you plot this Hall coefficient, so that is 1 over Ne. So then actually Hall resistance, so rho h. So that is directly proportional to B. If you plot as a function of B, you will see Hall resistance is a linear function with B. So you have to remember this one. So when you look at the quantum Hall effects, this Hall resistance will have some steps. So we call the Hall plateaus. So in the classical case, you see this linear B dependence of your Hall resistance. Okay. So now if you do this one in little more details, So we know the E is rho times J, because the way we define conductivity and resistivity is little different. So how do you define the resistivity? We write, if you change your J, we need to know how the electric field is changing, right? E equals rho times J. The way you define your conductivity is when you apply electric field, how the current density changes. So that we define J equals sigma times E. Then also in more general term, we can define your rho H as actually that the whole resistance is whole coefficient times H. Please remember that one. Whole resistance means that has the dependence of H, because RH is only 1 over NE, right? It doesn't have H dependence, but whole resistance is basically whole coefficient times H. Then rho H is, if you remember, that's the whole the resistance is given by this whole potential difference, whole voltage divided by the longitudinal current, right? That's how we got this H over NEC. So if it is a two-dimensional case, this is basically N of the two-dimensional one. So now important thing is this rho and sigma, they are really tensors, right? So in two-dimensional case, we can write rho as the 2 by 2 matrix, right? So rho xx, rho xy, rho yx, rho yy. So then you can write this equation, E equals rho j, you can write as this is a vector, ex, ey, you can write as this tensor as this 2 by 2 matrix, then your j is this one. So if you solve this one, so we can easily write this equation. So it's coming from, so this we already did this one, right? How to get using the relaxation time approximation, we knew how to calculate sigma Ex and Ey. In the previous slide, we showed this one. So now if you write Ex separate like this, so now I can write in this form. So using these two equations, we get Ex, Ey. Now I can write the vector Ex, Ey. So then your matrix elements will be, you can see if I take Jx, Jy as your vector here. So this is your rho matrix, right? So the rho is given by 1 over sigma 0, these numbers. Please start with this one. We already did using that relaxation time, dp over dt, that is 0, that's equals minus E plus V cross B minus P over tau. That you get this equation, right? So now you can see your what is your rho xx and rho xy, because this is rho terms, right? This is your rho xx, this is your rho yy. You can see rho xy and rho yx. So now if you go other way, so if you start with J, apply electric field and measure J, you can write Jx, Jy this way, right? Now I want to see how you connect this sigma to rho, because in general case, we say conductivity is just inverse of resistivity, right? But that is not true if you look at this in tensor forms, like if you have different component of x and y. So, but if you write it this way, we know sigma is given by this one. But if you take the not the number, you have to take the inverse of your matrix, right? So if it is a scalar, that's simple. You can write sigma as 1 over rho. But if it is a tensor, so your sigma is basically inverse of your rho. You know how to calculate the inverse function of matrix. You have to take the cofactor, then divide by the determinant, right? So everybody knows how to take the inverse of the matrix. So if you do that one, your sigma xx comes like this, because we know rho x and rho xy here. If you plug in these are the numbers, you get rho xx and rho xy, because we know how to write sigma xx from here how to write this one. Now, if you plug in your sigma xx, you can calculate what are the sigma xy, since we know rho xx and rho xy. So this is, you can see now in this equation. So even if your rho xx is 0, you have some sigma xx value, right? So here rho xx is 0. So then this term cancels, but you have sigma xy term. So that's a little bit, you have to understand how to relate your sigma values to your rho value. The rho values we know how to get from the, like in the previous case. Now, if you want to calculate your sigma, you can see how they change with your cyclotron frequency and the relaxation time, and of course with the Drude conductivity. Now, still this is in this situation. So, but if you consider real two-dimensional situation, actually what people have seen is this quantum Hall effect. So, like in the classical situation, we have remember your the whole resistance rho xy, right? Remember, you have to understand this, what is xx and xy. If I have current in this direction, that is x direction, right? If I measure my voltage in the same direction, like here, so that means your x and v are in the same direction, then what we are measuring is rho xx. But if you want to measure rho xy, you pass your current this way in the x direction, but you measure the voltage across y, like this one. That is we call rho xy. That is the whole voltage. This is your longitudinal resistivity, rho xx. This is your whole voltage, whole resistance, rho xy. We know rho xy, if you measure with magnetic field, there classically it shows this linear relationship, right? So, but rho xx, basically that is what we expect is this sigma 0, the something called the Drude conductivity. That's what you expect. You see this linear relationship, then you see this constant sigma 0. But if you go to very high temperature, sorry, very low temperatures and very high magnetic fields, so instead of this constant sigma 0, it's starting to go through some oscillations. So with periodic oscillations at the same time, so this will starting to show some steps. That is the whole quantum Hall effect. So you can see how these are measured, right? So I is going this way, magnetic field here. So if you measure voltage across this one, that is the rho xx. If you measure the voltage across these two, you get rho xy. So you can see here, so very nicely you have these oscillations. These are very large magnetic field, up to like 10 Tesla. This is small magnetic fields, right? You can see, so this, you have some regions, your rho xx, so they become 0 here, right? So then you have this nice peak, then it becomes 0 again, so then peak, so then it's long 0, then you have peak. Whenever it becomes the 0, your rho xx, the rho yy, remember it's supposed to be the straight line, they show this nice plateau. So every time this rho xx becomes 0, this one shows a plateau. So this is the quantum Hall effect. So we actually starting from this, if you measure in unit of this E squared over H, this is like first plateau we call this I equals 1, then second plateau happens at I equals 2. This exactly, this becomes 1/2 of this one. Then this is like 1/3, that's I equals 3, I equals 4, like that. So these are called quantum Hall steps. So actually that's coming because we know even if your rho xx 0, you have rho xy coming from that relationship. We know how to calculate rho, if you know, or sigma from your rho xy and rho xx. So actually this is mostly coming due to this the Landau levels, because if you take simple under magnetic field, you have something called this Landau levels, right? That energy of Landau levels given by n plus half times your h cross times your, this is the cyclotron frequency. So this happens for n equals 1, n equals 2, n equals 3, like that. So these are equally spaced energies, right? So the distance between two energies is given by this EB h cross divided by 2m. So equal space. That's why we have this quantized plateaus here. It's going from n equals 1. So typically the whole resistance is given by this one, right? So that is this linear region. But at high magnetic field, this typically low fields, your rho x is given by this Drude conductivity, 1 sigma 0. Then the whole field is given by this h, that's the linear dependence, right? But high fields, you will see this rho xy shows this e squared over h times this we call this coefficient for the whole effect. So this typically this n value is integers. So you have n equals 1, n equals 2, n equals 3, like that. So but later on, even at further high magnetic fields going to like 30, they found even whole plateaus with this n value is fractional values. You can see like, so going from this is like n equals 1, right? So that's what we found here. But you can find something like 4/3 or 5/3, 2. 2 is the integer one, right? 2, 3. But in between, you will find some other values like 4/5, 2/3, 4/3, many fractional values. That's called the fractional quantum Mole effects. Typically, if you, this is your rho, right? If you write in terms of sigma, that is n times e squared over h. So n goes from 1, 2, 3, like that for the integer quantum Mole effect. But for fractional Hall effect, they can be fractional values like 1/3, 2/5, and things like that. This is a fractional quantum Hall effect. So now you understand the classical Hall effect, that basically you have this linear rho xy and with respect to b and constant rho xx given by Drude conductivity. But high magnetic fields, you will see these oscillations, like, and so whenever this rho xx becomes 0, you have these quantum plateaus. So that plateau will correspond to this sigma xx given by this special unit called e squared over h. It can be integer numbers of that we call the integer quantum Mole effect, or n can be fractions, we call the fractional quantum Mole effect. Now this is what people have seen for mostly two-dimensional electron gases. So basically electron is trapped between this two-dimensional plane in like quantum devices. We call this gallium arsenide, aluminum gallium arsenide. They are called the quantum well structures. It's mostly the multi-layers of gallium arsenide and aluminum gallium arsenide. So at the interface, you have this two-dimensional electron gas. So that's where we are seeing this quantum Hall effect. But graphene, so graphene is also a two-dimensional carbon material. So that means your electrons also you can consider as two-dimensional gas. but in graphene, that quantum Hall effect is slightly different. So that's real exciting. If you look at graphene, so they do the same thing, right? So you have this graphene layer, then they pass the current this way. Then if you measure the voltage the same direction, you get the longitudinal or the rho XX. If you measure the voltage across this one, that's the transverse, right? So then you get Hall voltage. So when they measure, actually instead of magnetic field, they apply a constant magnetic field like 14 Tesla. Then they change the current density, the charge density N, by changing this gate voltage. So by applying voltage to the gate, you can provide more carriers to the graphene. When they change the carriers, they can provide either positive charges, we call the Hall doping, or they can provide more electrons, that's we call the N-type doping. So that we can do by changing the sign of this gate voltage, right? When they did that one, they can see your rho XX. So they show this nice peak, just like you see in the quantum Hall effect regime. So then you have the regions where the rho XX becomes 0. So whenever they become 0, you see nice plateau here. You can see here you have this 0, then you have a plateau here. Then again you have a plateau like that. So remember, in the classical situation, so we saw these numbers come in like E squared over H times N equals 1, 2, 3 like that. But in the case of graphene, it's very interesting. They come not E squared over H, it's like 4 E squared over H times. The numbers are like half, 3 half, 5 half, 7 half like that in both directions. So that is really exciting. So then people try to understand that, because in graphene, they are, remember, they are Dirac fermions, right? They are not a simple fermion. So that means they have relativistic properties. So that means your Landau levels are no longer this equally spaced. So remember, Landau level, they went like directly proportional to n plus half h cross this omega c. But for graphene, since they are relativistic particles, your the Landau levels go like square root of b. So that means these levels are not equally spaced. You can see, because since they are square root of b, when you go high, they get close and close. So that means they are no longer equally spaced Landau levels. So this is one reason. Another reason is, so remember, for typical situation for quantum Hall effect, sigma xy or 1 over this rxy. So that is given like n times E squared over h, right? So but now what we are seeing is 4 times n plus half E squared over h. So this is very different from this classical standard two-dimensional gas Hall effect. That's because remember we talk about something called the pseudo spin, right? Because we have this in graphene, we have 2 sublattices, A sublattice and B sublattice. So with that, we found that corresponds to something called the pseudo spin. So now you have 2 terms coming from the electron spin, and also 2 coming from the pseudo spin term. So that's why you have this term 4 coming here. Then so you have this pseudo spin rotation. Because of that, instead of n, you get n plus half term. So that's why you see this change. You can see this this number is 4 times E squared of h, compared to two-dimensional gas. You have E squared of h. You have now 4 times that. Then also you have this additional half terms coming. Instead of 1, instead of 0, you get half. Instead of 1, you get 3 half. You can see how the things change for graphene. So that's mostly due to this additional degree of freedom coming from the pseudo spin. So this is a very important difference between graphene and two-dimensional gases. So another thing to remember is if you take bilayers, if you take 2 layers of graphene, if you do the same experiment at high magnetic field and if you change your charge density, now you will see in the same unit 4 squared over h. Now you see 1, 2, 3. So this bilayer means now you don't have the effect coming from that pseudo spin. They cancel each other. Now you see this is exactly what you expect from. So still you have additional effect coming from that pseudo spin in addition to the spin, but you don't see that pseudo spin rotation term in plus half. You get only n terms here. So this is coming from the bilayer graphene. So this is standard monolayer graphene. This is very interesting and very distinct property of quantum transport in graphene. Now also graphene, actually, if you look carefully, they show this ambipolar transport behavior. Ambipolar means they respond to both positive and negative charges equally. So there are materials, if they are like unipolar, that means you can be only influenced by one kind of charge. If you can put like n-type carriers, so to enhance your properties, but the p-type carriers don't influence that. But graphene is ambipolar. That means you can dope with both electrons and hole, because we know at the Dirac point they are neutral. I can dope with electrons so that Fermi energy can be moved to this conduction band, or I can dope with holes that will move your Fermi energy in the valence band. But you can move from one band to other band through the Dirac point. So that's what this one shows here. So here you can see this is more like your Fermi energy is at the 0 point here. Now if I change my carriers going positive direction, that means you are going in the valence band in this direction. You can see your mobility here. So that is charge carrier density. So they are changing this direction. Then also I can dope by moving my Fermi energy in the negative direction. So that means you will see they are pretty symmetric, right? That means you can dope it with both electrons and holes. Then also here it shows how the conductivity changes. So you can see, so you can change your conductivity by doping with both applying positive voltage. That means you are applying more negative charges, or applying negative voltage. That means applying positive charges. In both ways you can make your conductivity changes, but also you can see it goes through a 0. Yes, so 0 means it's going through this Dirac point, right? It's starting from this negative. So then it go through this Dirac point, it becomes 0. Then it goes to the other band. So that's why you see this kind of behavior. Then also if you look at your, so this is again, it shows this similar behavior for different temperatures. So this one shows the Hall coefficient. You can see Hall coefficient. Like I said, Hall coefficient is a measure of your charge carrier type, right? You can see here your Hall coefficient is positive. So this is 0. So that means your Fermi energy is in the valence band, right? So now if I go from here by doping this way, it goes to 0. So then it becomes here exactly 0. Then when it moves to the conduction band, you can see it is coming to negative and stays negative. That means your Fermi energy is now in this direction. This is very important for graphene. You can charge graphene either n-type or p-type. So that's why we call this a ambipolar transistor. So then also graphene, like, yeah, here, this is exactly what I was trying to explain, right? So by that was mostly doping by electrical gate, but you don't have to do that way. You can even do chemically, right? If I introduce some chemical agents, so there are things like electron donors and electron acceptors. Electron donors means they will donate electrons to graphene. For example, if you take ammonia, ammonia is a good electron donor. It will donate electrons to the graphene. It's more like applying a positive gate voltage. By applying positive voltage, you provide electrons to the channel. By applying negative gate voltage, you provide positive charges to the channel. So, but in the case of chemicals, so you can do the same thing. So suppose you initially your Fermi energy is here, right, at the Dirac point. But if I this is the intrinsic case, if I functionalize with N-type dopant, so that means I can move your Fermi energy to the conduction band. So by if I dope with some acceptor, that means a p-type dopant, you can move your Fermi energy to the valence band. You can see initially it is here, N-type doping, you make it move into N direction, and by p-type doping, you move your Fermi energy to the positive side. That means this direction, right? So then these are, you can see initially the crystalline graphene, like I said, that has ambipolar properties, right? You can have your the conductivity changing for both negative and positive the direction, but crystalline graphene, as prepared graphene, people have found that to be p-type. I think that's because they already get p-type doping because of the oxygen and moisture in the atmosphere, because that you cannot avoid, right? Once you make graphene, when you take it out, so it's always exposed to air. So air has this oxygen and moisture. So that will, oxygen, we know that's a electron acceptor. So that means they will take electrons from the graphene, making it p-type. So that this shows more like a p-type behavior. P-type behavior means they are not exactly symmetric. This has more voltage or the conductivity for N-type. N-type means, like I said, this gate voltage. If I apply negative voltage, it will provide more holes to the system. You can see since this has higher value in the negative direction, this is a p-type material. But if I heat anneal in ammonia, so ammonia will provide more electrons because some of these carbon atoms can be replaced with nitrogen. So in the process, it will donate one electron to the graphene, so that makes it more electron rich. So in that case, you will see more higher conductivity in the positive side, like compared to this point, and this point is higher, right? Here, compared to this point is higher. This is we call p-type. Here, we call it n-type. This we can dope with donor materials. So also we can do this is more p-type if you I think react with something like more accept molecules like nitrous oxide or some other strong oxidizers. Okay, so then yeah, this is what we talk about the gate effect on monolayer, right? So basically, by applying this gate voltage, you are providing more charges to the system. If you have negative voltage, so that means in your capacitor you apply positive voltage. That means your the graphene becomes N-type, right? Because that's the other plate of the capacitor. So that's why they become p-type. If I apply positive gate voltage, it becomes n-type doping. Also, please remember the number of electrons is given by this equation, right? So then also we know your Fermi energy is given is a function of square root of your charge density. So you can see by applying gate voltage, you can make your Fermi energy to shift from Dirac point to either in the direction of conduction band or in the direction of valence band. Actually, it can be shifted by almost like half electron volt if I apply gate voltage of about 50 volts. So that's, you can easily tune your properties by changing the gate voltage. Also, you need to understand if my Fermi energy is, suppose this is my Dirac cone here. So suppose if my Fermi energy is at this point, so that means, so electrons are filled up to this point, right? You can only promote electrons going from somewhere this unfilled state, so filled state to unfilled state, right? So here it is filled up to this red part. So you can only promote from here to here. You cannot promote one from this filled state to another filled state, right? You need to have, sorry, unfilled. These are the unoccupied state, right? You need to have unoccupied state and occupied state. So only you can promote from occupied state to an unoccupied state, not from this point to this point, right? You can see again here, this is not allowed. This X is across, it doesn't work, but you can go from occupied to unoccupied here. So both these are not allowed because you need to have unoccupied state and corresponding occupied. So this is fine, right? You can do from here to here, but none of these. This is important thing to remember. So then a little bit about the band structure of bilayer graphene. If you have two graphene layers, so suppose this is a monolayer, right? You have just simple Dirac cone. So this is Fermi energies here. That means these are all filled. These are all unfilled. These are unoccupied state. You can always fill from occupied to unoccupied. But if you have a bilayer graphene, actually it will open up a gap. So typically, so this is your K point here. So in addition to this Dirac point, now it doesn't have the real Dirac point. So it becomes more this parabolic bands here. So then you can have some transition coming from this. So then you have the sub bands, right? So you can have some transition coming from this sub bands. So we call this kind of, so it's a Van Hout singularity. Okay, so that's yeah, you can see what happened. The bilayer graphene with some gate voltage. So in the this bilayer graphene, so in the pristine without any gating, so you can have this Van Hout singularities. Then we have these sub bands coming due to this layer interaction. So these are no longer this Dirac cone. So these are already the parabolic bands. So now if I apply a gate voltage, you will see this the bands. These are more like semi-metal bands, right? So they actually split. So they are more like removing the degeneracy. They are actually opening up some gap. So still this is a zero band gap, right? But they are not Dirac fermions. So by applying a gate, so it will open up a gap between these first two bands. So even this the bilayer graphene, these are like two layers, right? So you can dope this bilayer graphene by both P and N type. So if you take bilayer graphene, if you do the gate voltage dependence, you can see it shows quite bit mono and what is called the ambipolar behavior, right? But still this shows little bit more p-type because of this doping in the atmosphere due to oxygen and moisture. Now, if you take this same bilayer material, but not just sorry. So actually here we are comparing monolayer, bilayer, and some few layers. So this black one is the monolayer one. You have only one graphene. That means you have this Dirac cone structure. You see this more ambipolar behavior, but still little bit p-type because of the air doping. But if I take a bilayer, two of them, that shows actually more p-type, right? Because that's because of this, it's opening up a gap due to the gate voltage. So initially it has more like ambipolar behavior, but it opens up a gap. Because of that, it shows more this p-type behavior. But if you take many, like few layers, not just two, maybe about 5, 6 layers, then it shows mostly like p-type behavior. See, you can see it doesn't have any. That means you are opening up a bigger gap. So then it becomes more like a standard semiconductor kind of behavior. Okay, so that's then last thing I want to talk a little bit about Raman spectroscopy of graphene. So if you take Raman spectroscopy, then again we are looking at this Raman spectroscopy is the inelastic scattering, right? You just shine with some laser with some frequency, then you are looking at the backscattered light. So that the frequency is modified due to the inelastic scattering, right? It's mostly coming from the difference is the phonon modes of the graphene. So this mostly this carbon-carbon the vibrations. So if you look at typical graphite, so graphite has this something called this very strong we call the disorder band. So this is called D band that comes around. No, sorry, actually this is we don't see the that comes a little bit. So you can see for graphite has this we call this G band. G band happening around maybe 1580 centimeter inverse. So that is very sharp and strong. So then we have the secondary mode of that we call that D band I was talking about, that the disorder band that's coming around 1300. So this is the second order band of that disorder band that's coming around 2600 here. So this is taken with the laser wavelength of 514 nanometers. So if you take graphene, the graphene is only monolayer of this graphite. This G band becomes kind of weak, but the 2D band we call this second node of that disorder band, that becomes really strong. So this is more than 2 times stronger than your G band. So then if you, here is some more details here. So you can see the D band I was talking about. So that is in the 1300 nanometer. That is also pretty weak, but still it is apparent here. So this is the G band like we were talking about here. So that is about 1600 centimeter inverse. This is this second order D band. Actually, it's the second harmonic of this D band. So that is 2D. If you take monolayer graphene, so this is how we usually find the quality of graphene. So your G band and your 2D band is almost more than 2 times stronger than the G band. So if you go to bilayer graphene, so this your the ratio between this 2D band and the G band is getting little bit smaller than your monolayer. But if you go to 3 layer or more, then your D band disorder band also grows. Then this 2D band and G band ratio also getting smaller. So this is actually graphene grown from this chemical vapor deposition, and this is coming from that Scotch tape techniques, mechanical exfoliation. Actually, these have much better quality because here you have some impurity. That's why your D band is visible here, but for the Scotch tape technique, you don't see that D band at all. So also you can see here. So when you go to different levels, your band ratios also changing. You can see for monolayers, your Ig is much smaller compared to this 2D layer. 2D is much higher. So, but when you go to more and more layers, that ratio becomes smaller, right? So that's one signature how to understand this quality of your graphene. Okay, so I'm going to stop here. So then I have just one more last lecture based on topological insulators. Okay, thank you.